Thank you all for coming. Thank you, Professor Manca, for the nice introduction, and also the other jury members for accepting the role of evaluating my work. So as you can see from these slides, there's Thèse involved, so it's natural that we're going to talk about industrial applications, not any industrial applications. Today we are talking about, cargo inspection that has a lot of interest for border control, as you can imagine. Today, this is what a cargo inspection machine looks like. So you have a gantry, which is composed by an X-ray source, which is, it's made of a linear accelerator, conventional electron accelerator, that allows to produce X-rays. These X-rays are subsequently collected with a detector, and these are the sort of images you can obtain. Those are 2D images, 2D radiographies, so it's actually easy to elude this sort of control. So can we do better? Can we do 3D tomographies? We would have to do something like this, which is not impossible, but it's very, very difficult, very challenging, because you will have to motorize tons. You need to motorize both the detector and also the accelerator. So, of course, we ask ourselves, can we do even better to get 3D tomographies of the contents of these cargoes? And one solution could be using multiple small sources that surround the cargo like this. So we would have a sort of static gantry, and inside of this gantry you can see multiple LPA-based X-ray sources. It's here that we start talking about laser plasma accelerator, because this sort of technology allows us to decrease, to have a huge gain in terms of the size of these accelerators. So, and of course, if we can do that, we will have static gantries, which means that we don't have to motorize anything. So the system will be actually cheaper and also lighter. And this is sort of the mission of the Multi-Scan 3D project. As you can see here, this is the page of the website. Feel free to check it out for further reference. And now, what kind of gain are we talking about in terms of size? Here you can see the comparison between what is the world record obtained with the laser plasma accelerator. It's a very interesting, fascinating result, where researchers were able to accelerate electrons to around 8 GeV in just 20 centimeters of plasma, so very, very short distance. While this is the sort of reference of the scales of a linear accelerator. In order to get 50 GeV, this is the SLAC accelerator in the United States. You see this that looks like a road. This is actually the accelerator, which is around 3.2 kilometers in length. So we have a gain of around 3 to 4 orders of magnitude of the accelerating gradients with laser plasma accelerators, ultimately allowing us to really have a more compact accelerating systems. Now, many of you are already acquainted with the notion of a laser plasma accelerator, but for those of you that are not, what is exactly a laser, and what kind of lasers do we need to do this sort of acceleration? What also is a plasma? So here you can see a picture of the titanium sapphire Saljon laser system. It's actually the laser system I used for the experiments in my thesis, during my thesis. And it's a very big laser. It takes like a whole room. And it's a super-intense laser. That means that it's so intense that it's capable of, once focused, to ionize a gas, producing a plasma, which is, the easiest definition we can have of a plasma, I guess, just an ionized gas. And since these laser systems can produce such intensities, we can do much more than just ionize the gas. We can also accelerate electrons. How? Now, the best way to visualize the sort of physics we are talking about comes, in my opinion, from looking at 3D simulations, which is also a huge part of this thesis. So on a macroscopic level, what we are simulating, it looks something like this. So you see we have just some optics focusing a laser pulse onto a gas that once ionized becomes a plasma. Then we accelerate electrons. So this is the sort of setup you will see several times in this presentation. And this, on a microscopic scale instead, it's what happens, at least from a simulation point of view. What you see here is The red color map, it's the laser pulse, which is propagating towards, let's say, the right-hand side of the slide. And we are looking at it in its frame. So this is why it's not really moving, because we are looking at this simulation, it's in the laser frame. And the gray color map instead are the plasma electrons. As the laser crosses the traverses the plasma, it's pushing electrons away through the action of the ponderomotive force. So it's pushing electrons towards regions of decreasing laser intensity. Now, to have a better view of the sort of trajectories of the electrons, this is what happens. So we have two electrons. As the laser is propagating, they receive this sort of ponderomotive push, which is very important. The ponderomotive force is sort of the hero of this presentation, as you will see by the end. And these electrons are gaining, are getting pushed by the laser. And just behind the laser pulse, we just have positive ions, because of course it's a fully ionized medium. So we have ions, and these electrons feel the recombination force of these ions, and they start oscillating in the radial direction, as you can see. If you combine this radial motion with the longitudinal one, you get these sort of bubbles, these sort of cavities in plasmas. And this is very, very important, because again, if we focus on just one bubble, what I just described looks sort of like this. We have again the laser, which is propagating towards the right, on the right-hand side of the slide. We have an electron sheath that is surrounding this positively charged structure, cavity, and charge separation means that there's an electrostatic field. And if we could visualize the sort of field, it would look something like this. So in the longitudinal direction, so along this axis, we would have this field, which is called wake field, because it's the plasma electric field induced by the laser in its wake. And now, if we could inject some electrons here, which means in the accelerating phase of this electric field, I mean, it will look something like this. They can co-propagate with the laser pulse inside of this structure, and what you can produce is something like this. You see, these are 10 shots, 10 energy spectra that were obtained 2-3 years ago here at LOA. This is a result of my group, UPX, where electrons with energies around and also exceeding 1 GeV were obtained in just 1 centimeter of plasma. So it's a huge gain in compactness compared to conventional accelerators. Coming back to what I was saying at the beginning, just to conclude, we now have a better grasp of what a laser plasma accelerator looks like. And now a laser plasma-based X-ray source would be something like this. We will have a small vacuum chamber hosting some optics that allow to focus a laser pulse, again, in a gas that's getting ionized by the laser itself, so it becomes plasma. We accelerate electrons. We use a Bremsstrahlung converter, which could be in tungsten, for instance, and subsequently we are able to produce X-rays. So, what are the objectives of both the Multiscan 3D project and my thesis? So, in order to make this device possible, the partners of the Multiscan 3D project define the requirements, the needs, in terms of average current, and this is clearly linked to the title of my thesis. We need average currents per source exceeding 1 microampere, as you can see here. Current laser plasma accelerators usually produce tens of nanoamperes, so 1 microampere is quite an improvement, and ideally we also want electron beams with energies below 10 MeV for radioprotectional issues. Now, regarding the 1 microampere milestone, let's say that's going to be achieved working on 2 different fronts. We need to improve both the laser system. We need to gain a factor 100, a factor 10 on the laser average power. Current laser systems have average powers of 10 watts. We need to get to 100. And there's an ongoing project between Thèse and Laboratoire d'Optique Appliquée, specifically to develop what is called Heracles laser, which would be a 100-watt laser system. This is not really what I do in my thesis. What I did was the second front, the improvement of the charge per joule. It's very simple to get the requirement, the need in terms of charge per joule from the average current and the average power of the laser system. So in my thesis, what I actually did is really working on improving the charge per joule of these sources. And what I did specifically in order to study and achieve this result was both working on experiments and that motivated particle in cell simulations, and vice versa, particle in cell simulations then allowed me to understand what I was doing with the experiment in terms of physics. In my manuscript, you can also find some other side quests, let's say. I also had to work on plasma source development. You have here the silica nozzle that I developed and that was subsequently produced by the FTMC lab in Lithuania, one of the partners of the Multi-Scan 3D project. And I also worked on developing energy spectrometers. So actually these are dipoles. This was the dipole I used during my experiment. And since I recognized some limitations with this system, I proposed an improvement and I developed this second spectrometer. I don't really have time to get into the details, but if you have questions, feel free to ask. Now we are ready to start discussing the experimental part. This is the experimental setup, which is, I think, very, very simple. We just have a laser pulse focused with an off-axis parabola, over 4 parabola. The experiment was performed in Sargon, so we had a 60 terawatt titanium sapphire laser capable of producing laser pulses with a wavelength of around 800 nanometers, duration of around 30 femtoseconds, which means, very, very short pulses. And the laser was focused, again, with the f/4 off-axis parabola down to a full width of maximum diameter of 5 microns. This laser pulse, the driver, impinges on a nitrogen gas jet that was produced using 2 nozzles. These are the 2 nozzles. Let's say these are the external diameter, the exiting diameter of the nozzles, 2 millimeters and 4 millimeters. The second one is the one I showed you before. Then the produced electron beam was collected using a circular scintillator, which was a Lanex screen. And using a CCD camera, we are subsequently able to collect the emitted light. We have these sort of images that allow us to measure the beam charge and divergence. And this is what I call beam profile monitor. This is one of the made diagnostics that was motorized. So I could remove this scintillator from the laser axis and place the electron spectrometer, which again is composed by a small dipole and a small rectangular Lanex screen, as you can see here. And again, using a CCD camera, we can collect the light and produce these images and deduce the energy of these electrons. We also had a second laser beam, the probe beam that you can see here, which is perpendicular with respect to the driver beam. And that basically allowed us to to measure the plasma density using a physics camera that again was placed outside of the vacuum chamber. These are pictures taken during the experiment. This is the vacuum chamber, which measures around 1 meter in diameter. You see the driver trajectory, just for simplicity. I think what is more interesting is the picture on the right-hand side, where you get a close-up of the 2 diagnostics I described. Here you have the driver impinging on the gas jet produced by this nozzle. The electrons are sampled using a pinhole in front of the dipole, and then subsequently deflected onto the scintillator. We could remove the scintillator, the spectrometer following the direction of the green arrow, and place the BPM, beam profile monitor again, closer to the nozzle in order to perform charge measurements. And this is a first characterization of the beams we were able to produce. This was obtained using the bigger nozzle at around 30% of the critical plasma density, so the densities are normalized with respect to this value. And this image in particular of the BPM was obtained using a 1 joule laser pulse. And just to give you an idea of the sort of electron beams we are dealing with, these are very huge, very divergent beams. We estimate a full width of maximum divergence of around 300 millirads. So these are, again, very huge compared to usual laser plasma accelerated electrons. And also the charge is this is the highest we were able to measure, 30 nanocoulombs. Maybe this scale doesn't really allow you to understand what kind of beams we are talking about. It was this big. It's 7-8 centimeters of diameter. So, I mean, very huge beam. And on the right-hand side, you see the energy spectrum obtained with this nozzle for different laser energies. You see that changing the laser energy doesn't really seem to yield much of a difference in terms of the shape of these energy spectra that have around 5 MeV in average energy. And we estimate about 10-15% of the charge collected on the spectrometer to be above 10 MeV, which is not great if you remember the mission of the multi-scanton project. Since this spectrometer was motorized on the along the horizontal direction, I was also able to sample the energy spectrum at different horizontal positions. So you see these colored circles that are coherent with the colors of these energy spectra. It's pretty clear that as you move farther away from the laser axis, you get lower energy electrons. This is also quite interesting because it could propose some solutions to the 10 MeV issue. Now, in order to have more information about the whole measurements we performed, I'm going to show you actual plots of the charges per joule we measured. But first, please keep in mind that the BPM was placed at 2 different positions compared to the gas jet, ultimately yielding 2 different collecting angles. This is very important. So we had a 0.25 and 0.5 steradians collecting angle. These are the charges per joule, actually per steradian, so be careful. We measure during the experiment using this, the smaller nozzle on the left, and the bigger nozzle on the right. And be careful about the collecting angle because it's not the same, 0.25 for the smaller nozzle, 0.5 for the bigger one. Each curve refers to a different plasma density, as you can see here again expressed as a fraction of the critical plasma density. And with the smaller nozzle, I was actually able, you can already see some numerical results. These dashed curves have been obtained using FVPIC. So these are numerical simulation results. And from these plots, we can already see 2 main effects, except for this curve at the lowest plasma density we measured. It seems that the charge per joule initially increases with the laser energy, and then it seems to decrease, which is kind of interesting because it means that we have an optimum condition. And what I find even more surprising is the charge per joule saturation effect that it's pretty clear we see here. Look at, for instance, these 2 curves, the green one and the blue one, which are at 2 and 5% of the critical plasma density. Above a certain laser energy, we see that increasing the plasma density by a factor of 2.5 doesn't yield much of a difference, which is, I mean, again, very interesting. You get something similar even with the bigger nozzle, so it seems to be consistent. What about the maximum charge per joule we obtained? We measured around 21 nanocoulomb per joule with the smaller nozzle, and I estimated a 6% efficiency, conversion efficiency, which is defined over here. I hope you can see it. It's the ratio between the total electron energy to the total laser energy impinging on target, expressed as a percentage. 6%, it's a very big value compared to usual laser plasma accelerators, which is usually, again, few percent. With the bigger nozzle, we did even better. We measured 35 nanocoulombs per joule. It's this point over here, with a conversion efficiency of around 14%, arguably one of the highest ever measured, maybe the highest ever measured experimentally. Before moving on to the second part, which has to do with the numerical simulations, I want to just summarize the main findings. So we were able to prove some effects, to observe some effects of the charge per joule against the laser energy. We observed a maximum of the charge per joule. The maximum we measured, it's around 35 nanocoulomb per joule, which is great because we were looking at getting something around 10, and we got almost 5 times, so great for the multi-task entity project. And we got an efficiency of around 14%, and we believe that we could have done better during the experiment because the deformable mirror didn't really behave during the experiment. So we think that improving the focal spot, and here you see an example, we could get an efficiency of around 20%. This seems to be consistent with the numerical simulations I will show later. And about the energy spectra, we had those large quasi-Maxwellian energy spectra with average energies around 5 MeV, electrons exceeding 10 MeV. I mean, that's bad for the multi-task 3D project. And ultimately, I was also able to prove that if we measure the electron beam, if we start measuring electrons, more divergent electrons, we ultimately see that they are less energetic. And now we can start discussing about particle insert simulations. And during my thesis, I mainly focused on 2 sets of simulations. The one on the left, which is closer to the experimental configuration, and the one on the right instead, which is I consider to be idealized configuration, where you have this linear ramp leading to a constant plasma density profile, really just to grasp the main physics of these configurations. And here are the results with the first set of simulations, so the one that is supposedly closer to the experimental conditions. And what you can see here, these 2 images are angular distributions of, again, numerical results. These are numerical equivalent of BPM images. And for 2 configurations, same plasma density, 5% of the critical plasma density, but 2 different laser energies. Because what I really wanted to understand is the decrease of the charge per joule. And here, what you see is that if we measure the charge inside the collecting angle of 0.25 steradians, which is again coherent with what we did experimentally, we see a decrease of the charge per joule per steradian, increasing the laser energy. So it seems to be consistent again with the experimental findings. And it seems, I mean, I think it's clear that if we had a bigger collecting angle, we would have been able to collect more electrons, and we would have not observed such a huge discrepancy, such a huge difference. So this is why I got to the conclusion that probably this is due to the fact that increasing the laser energy yields more divergent electrons that are not ultimately collected by the BPM. And here you can see, again, these 2 angular distributions. In this case, it's same laser energy for 2 different plasma densities, and again, seems to be pretty consistent with the experimental findings. It seems that increasing the laser energy increasing the plasma density doesn't really yield a huge increase in terms of the charge per joule. And in order to answer these questions, why this happens, because these simulations don't really seem to be sufficient to understand what's happening, I relied on the second set of simulations, so the idealized case, and I was able to obtain this. Follow me, because it's not that easy. So this is the charge per joule that I obtained. So it's not charge per joule per steradian, it's really the total charge per joule on our 4 pi solid angle for electrons above 2 MeV, because we care about electrons with some energy to them for practical reasons. And so this map was obtained as the interpolation of several FAP simulations, where I just changed the plasma density, the horizontal axis, and the laser energy vertical one. And again, even if in this idealized configuration, we see that we have a sort of saturation effect. Why? You see these white lines. These are curves at constant values of the charge per joule, and above a certain plasma density and laser energy, they start being almost horizontal. So again, even with this set of simulation, it seems that we have this saturation effect. If we start digging even deeper and looking at what's happening at the electrons, we get something like this. These are 4 energy spectra for 2 different plasma densities, 3% and 6% of the critical plasma density for 2 different energies, 1 joule and 0.12 joule. Now, it seems that the charge per joule saturation effects comes from this, the fact that for 2 different plasma densities, we have the same amount of electrons almost being accelerated to almost the same energy. So probably more needs to be done to understand this mechanism, what's happening, but it's pretty clear from this. For instance, in the 1 joule case, it's very, very clear. You see these 2 spectra superimposed despite the huge difference in plasma density. There's a factor 2, and we get the same amount of electrons, again, practically at the same energy. So now we get almost to the last part of the presentation, which is a personal favorite because it has to do with the acceleration mechanisms. Since we have this huge energy spectra, we also asked ourselves what's happening, how do we accelerate these electrons at such different energies. And in order to describe this, I need to provide some further background, and specifically I need to recall what's happening while the laser is propagating in nitrogen. So you see here, nitrogen has 2 different electron shells. The innermost one, it's made of 2 electrons, and the outermost one has just 5 electrons. And on this table on the bottom, you can see the ionization thresholds of these 2 shells expressed in terms of the normalized vector potential. And they've been calculated using the ADK model. And you see that there's a huge difference in terms of ionization thresholds. And this is very, very relevant in terms of the dynamics of the electrons as the laser propagates in plasma, as you can see from this animation on the right-hand side. What you see here is gray electrons, which are L-shell electrons that get ionized closer to the laser leading edge, so where the laser intensity is not that high. They receive a ponderomotive force, and they tend to follow these trajectories, creating these sheath I mentioned at the beginning of the presentation. K-shell electrons, on the other hand, are getting ionized way closer to the laser intensity peak, and they tend to follow these more longitudinal trajectories, and they can be injected here at the rear of the cavity, experiencing what is called ionization injection. Now, with that being said, this is actually the result. The one example of a simulation I performed, again in the idealized case, using 1 joule laser pulse and 3% of the critical plasma density. The colors are coherent with the previous slide. So red color map, it's the laser pulse. Green, K-shell electrons, gray, L-shell electrons. And what's happening, it's very, very interesting and to an extent also unexpected. Compared to what I presented at the very beginning, we don't really see those cavities I mentioned, but rather we see a huge amount of K-shell electrons accumulating on axis. You see here at a certain point we have this huge like column of K-shell electrons on axis, surrounded by a sheath of L-shell electrons. And I try to highlight this with this snapshot, just removing numerically K-shell electrons. You see this sheath, this channel of just formed by L-shell electrons. And now this is very important because we are discussing the sort of cavities that can or cannot have a wake field inside. So indeed, such an accumulation of K-shell electrons on axis damps the longitudinal wake field, since if we have electrons, we are not really ensuring charge separation. In order to have a wake field, you need to separate charges. If you have electrons filling any sort of structure, you have a sort of extreme beam loading effect, leading to a damping of the longitudinal wake field. I think it's pretty clear if you look at, again, this plot on the right-hand side, where you have the black curve, it's the longitudinal wake field, which is very, very low compared to what you have at the front, where we can recognize a sort of cavity where the laser resides, because in here the laser still ensures a degree of charge separation. So at the front, we can recognize a sort of cavity with potentially a very intense wake field, and at the back we just have a fraction of what we have at the front, we have these rapidly changing modulations. Now, so these obviously raise some questions about how we accelerate these electrons. We were expecting something like this, which is the sort of scenario presented in the scientific literature, where you can read the fact that K-shell electrons are getting injected in multiple cavities like this, and thus they are getting accelerated by the wake field. But if you don't really have cavities, again, you're not really observing charge separation, you don't really have this sort of scenario, again, that was expected. So it's not really clear, but still these electrons are gaining some energy, so we need to dig even deeper, we need to see what's happening. And in order to find answers to these questions, I developed, along with Igor Andreas, the numerical expert here at LOA, this numerical tool, which we called FBP Electric Work Profiler. It's just a post-processing tool that's already available on GitHub, that allows us to calculate the work exerted on every tracked electron, exerted by the wake field and the laser electric field on every tracked electron. Now, here you can see first sort of acceleration regime I was able to recognize. There's a lot to unpack, so follow me. First of all, I call this acceleration process non-traditional wake field acceleration, and I will get to the non-traditional part at some point. So the top half of this plot is in blue, it's the plasma density. The red, I hope you can see it, this is the laser, while the bottom half, it's just the radial wake field that allows us to see the sort of structures we might or might not have. This is, again, very different from what you would expect in terms of cavities. I mean, if we had cavities, the radial wake field would look very different from this. And the black curve we see here, it's the trajectory of one electron. Now, again, it's falling to the back because this trajectory, it's in the laser reference frame, so of course, naturally falls to the back. Once it gets ionized, it crosses the laser pulse. You see these small oscillation and rapid oscillations. This is signature of an electron crossing the laser electric field, and then it reaches that massive channel I mentioned before, and where we can have, of course, this focusing field leading to these bigger radial oscillations. Now, this is what you can get with FBPIC. You don't really need to do anything else. With FBPIC EWP, you can get this plot, and allowing you really to understand who's accelerating these electrons. So the blue curve is the electron kinetic energy. The yellow one, it's the laser radial work. And the green one, it's the wake field longitudinal work. So once the electron is ionized, it's crossing the laser, as you can see again here, and it's obtaining, it's experiencing a ponderomotive push from the laser. So there's a contribution from the laser. However, as it gets inside of this channel, it's experiencing some longitudinal acceleration coming from the wake field, from those very small, rapidly changing modulations. So they can still accelerate the electrons, although it's non-traditional, because this electron, it's not in phase with the wake field. It's continuously falling to the back. So in this sense, it's a wake field acceleration, but it's non-traditional. So here we have another example of one acceleration regime I recognized. I would consider it to be way less exotic than the previous one. It's a direct laser acceleration. You find papers 20 years ago, even more, discussing this. So in this case, the electron is getting injected in that front cavity where the laser resides, where we have the laser. And as it's falling to the back and getting injected here, again, we have these rapid oscillations. Again, a signature that the electron is crossing the laser field. And then we see these bigger oscillations. What's happening is that as the electron is feeling more and more the effect of the wake field, these external field, the wake field, it's allowing the electron to get in phase with the laser electric field, and thus it starts oscillating in this manner with these way bigger oscillations, because we're reducing the slippage between the electron and the laser electric field, and ultimately this transverse momentum gets converted into a longitudinal one through the laser magnetic field, since it's an electromagnetic pulse, so there's a magnetic component, and this transverse motion, thanks to Lorentz force convective term that you can see here, again allows to convert this transverse momentum into a longitudinal one. And this is again pretty clear looking at this plot. Blue curve, electron kinetic energy, yellow curve, laser radial work, and green, again, it's the longitudinal wake field work. We see that the most important contribution comes from the laser radial work, and that allows to accelerate the electron above 75 MeV. The previous example was at, I think, 4 MeV, so it's a huge difference in terms of energy. Now, this is the last sort of acceleration process I recognized, which is ponderomotive acceleration. Here you see two examples, the solid trajectory and the dashed trajectory. In the first case, we have the electron falling to the back again, so it's getting this ponderomotive push again. However, it's also crossing a region where the wake field is focusing for these electrons, so it's counterbalancing the laser push, which points outward. So we have this sort of counterbalancing effect between these two fields, and this ultimately leads this electron with very, very low energy, which is around 0.4, 0.5 MeV. Again, because the laser is pushing outward while the wake field it's exerting a recombination effect. In the second case, it's somewhat similar. Again, the electron is crossing the laser. The electron is crossing the laser, so it's getting a ponderomotive push, but it remains closer to the laser axis. And in this case, the wake field effect is way less relevant, and it traverses, it slips inside this channel I mentioned before. It experiences these big radial oscillations, but it's not really interacting much with the wake field. You see the green curve again. So it's able to retain most of the initial ponderomotive push. Now, in order to sort of understand if it's either the laser contributing most to the acceleration of the electrons or the wake field, I introduced this parameter, hoping also to sort of distinguish the different acceleration mechanisms, but it's very, very difficult because it's, in most cases, we have a combination of these acceleration processes, so it's definitely not easy. Anyway, introducing this laser to wake field work ratio, T. If it's positive, it's the laser, which can accelerate in this regime either via DLA or ponderomotive acceleration, or it's if it's between -1 and 0, it's wake field acceleration. Again, there's a lot to unpack. This is the angular distribution I obtained with two simulations where I studied both K and L shell electrons. So the top half of this angular distribution pertains both K and L shell electrons, and we estimate that around 60% of the electrons are getting accelerated by the laser by the end of the simulation. And thus we have a 40%, which is still a huge portion, experiencing some sort of wake field acceleration. The bottom, and just to be clear, red electrons, laser, yellow electrons, wake field. On the bottom half, it's just simply color-based the energy of these electrons, allowing me, again, even in this case, to prove numerically that closer to the laser axis, we have more energetic electrons compared to electrons that are more divergent. But what it's more interesting is these two phase spaces, so Z minus CT, the longitudinal position of each electron inside the numerical box, and their energy. And again, they're color based on key. The top is about K shell electrons and bottom L shell electrons. And you can make a case for this expression, MEC squared AP max, to be the maximum ponderomotive push an electron can experience, where AP max is the maximum normalized vector potential in plasma. So doing this, assuming this range, again, I consider just electrons above 2 MeV, because again, it's not particularly interesting to consider electrons with energies which are too low anyway. Between 2 and 8 MeV, 8 MeV corresponds to MEC squared AP max. We have around 47% of the electrons, of K-shell electrons experiencing ponderomotive acceleration. Everything that falls above this threshold, let's say, which is mostly this trace you see over here, which is actually closer to the laser. I think you can see it here. These guys are experiencing DLA, and it's around 8%, and the remaining 45% are just yellow electrons experiencing some sort of wave field acceleration. For L-shell electrons, we have most of the particles experiencing ponderomotive acceleration, and just 17% of these electrons can somewhat interact with the wave field. And in this case, these particles are not really experiencing any sort of DLA. This brings me to the conclusion of this presentation. So I would like to summarize quickly the findings, the results I presented. So experimentally, we are very happy. We got the charge per joule we were looking for, actually probably more. I think this makes also a nice conclusion. It's not something I discussed during the presentation, but using the configuration I described today, my team here at LOA, UPX, was able to perform a first radiography. So they were able to produce X-rays and study this ion sample that presents a fracture here at the neck of this sample, this ion sample. So this is a preliminary result, which is very promising. I also presented a numerical study allowing to understand what's happening in terms of the tendencies we observed experimentally. And a detailed numerical study allowed us to recognize these acceleration processes and also the relevance of the laser through its ponderomotive push, through its ponderomotive acceleration. In the future, since we measured electrons above 10 MeV, we definitely want to find solutions to avoid getting electrons above this threshold, maybe also ways to control the divergence. We like big beams, divergent beams, but it's also nice to keep that in check, just in case. Here you can find a list of my contributions and publications. I have 2 more papers under preparation as first author. And this presentation was brought to you by the European Commission that funded the multi-scan-3D project and also this work. Here you can see the partners of the multi-scan-3D project. I want to thank the 2 groups I work with, Thales MIS and UPX here at LOA. I also worked with many people from the APLI group that I also want to acknowledge and thank. I want to thank again the jury, and thank you all for coming.